So we just showed an important theorem that for any linear system, there is either no solution, one solution, or infinitely many. Okay. Now, this theorem is going to take a look at the case where we have a system with a coefficient matrix A that is square, n by n, and invertible. And in that case, for each n by 1 matrix B, this will be the constants matrix, the system AX equal B has exactly one solution, and namely that's the solution right there. We've kind of already looked at this already when we first started talking about an inverse. But if we have a system that is, we say, a square system, which would be the same number of equations as unknowns, and that coefficient matrix is invertible, then we know we have exactly one solution. So the proof is this. We first show that x equal A inverse B is a solution to the system AX equal B. Okay, so we first show that. And the way to show that is simply to multiply this A inverse times B times the matrix A. I can regroup, right, associative property of matrix multiplication. A times A inverse is the identity. The identity times B is just B. And so that proves, right, AX equals B means that particular solution clearly satisfies the system. So it is a solution. Now, what do we have to do just to show that x equal A inverse B is the only solution? Because we said there's only one. Right, so this is a solution, but there may be others. Right? So let's let x sub 0 be an arbitrary solution. To AX equal B. Let it be an arbitrary solution, so just any solution. We know we have at least one, right? We've proved we have at least one, so let this be an arbitrary one. So that means A times x sub 0 is equal to B, right? Satisfies that equation. Well, again, we're told that A is invertible, right? So in that case, let's multiply both sides by A inverse, and this is what we've done before. This probably looks familiar to you. Multiply on the left by A inverse. Again, over here, I'm just going to reassociate. And of course, when I do that, A inverse times A gives me the identity matrix. The identity times x sub 0 tells me that x sub 0 is equal to A inverse times B. Right? And that's the end of the proof, because that shows me for any arbitrary solution, it must be of this form. And so this is the proof that for any square matrix where A is invertible, we have exactly one solution, and we know how to actually solve it. So for those systems, we can solve by matrix multiplication. Let me give you an example of that then. So let's illustrate this in the following situation, using the result of this theorem. This system here, right, of linear equations can be written this way. So this is what this means, right? What is the matrix A? It's the 3 by 3 coefficient matrix. Let's grab the coefficients here. Coefficients are 1, 2, 1 for x sub 1, 2, 5, 0 for x sub 2, and 3, 3, 8 for x sub 3. Right? Of course, x is the variables, the unknowns, x sub 1, x sub 2, x sub 3 in this case. And B is the constants, 1, 2, and negative 4. Right? Constants. Right? So this is what we mean, right? When we talk about a system, this is what we mean. Now, it turns out that this matrix A is invertible. And I'd like you to go through the inversion algorithm on this matrix. I just did an example in the previous set of lectures on the inversion algorithm and working an example, you should be able to find the inverse of this matrix. And here it is. Oops, -3 and -1. Okay, that's the inverse. And you can check and confirm if I multiply these two matrices together, I get the identity matrix. But since it is invertible by the theorem we just looked at, there's one solution to this system. And what is that solution? The solution, so one solution, right? The one solution is A inverse times B. Right? So I just take A inverse. And I multiply it times B. B I'll bring down here, 1, 2, -4. All right. And we can do this multiplication. It's row dot column, so I get -40 times 1 plus 16 times 2 plus 9 times -4. Right? And so on. 13 times 1 gives me 13. -5 times 2 is -10. And -3 times -4 is +12. And then the last row dotted with that is 5 times 1 is 5. -2 times 2 is -4. -1 times -4 is +4. And if I do those operations, I get -40 plus 32 is -8. And then -36 and -8 is -44. 13 and -10 is 3. 3 plus 12 is 15. 5, -4 and 4 is just 5. And so there's my solution. Remember, this is the x vector, which remember the x vector is x1, x2, x3. And so my solution is x of 1 is -44, x of 2 is 15, and x of 3 is 5. So this is a pretty good method. Now, it is not as efficient as doing Gauss-Jordan elimination or Gaussian elimination that we use to solve a system. There is one, and the reason is because finding this inverse basically requires you to do the Gauss-Jordan method, right, in the inversion algorithm. But if you have a system like this, but where the constants change, which is a very common actual situation and application, then this method is more helpful because the A is the same for all your systems. You have a one-time computational cost to get the inverse, and then you just multiply by B for each system to get the solution. So if you have a real large system, but you have hundreds and hundreds of equations systems of equations you need to solve where the B's are all different but the A's are the same, and then again they're square, A is square and invertible, then this method is more efficient. Okay, I want to close then with this connection between inverses and systems of linear equations. First, want to just share this theorem that comes out of I think section 1.6 in the book. Up to now, right, to show A was invertible, it was necessary to find the matrix B such that AB is the identity and BA is the identity. Right, we had to multiply both ways to prove that. But the following theorem now proves that A is invertible if we find a matrix B satisfying just one of these two conditions. Right, so if B is a square matrix satisfying B times A equals the identity, then B is A inverse. And similar, if we go A times B is the identity, then B is the inverse. So that's a theorem I'm not going to prove or anything, but that is presented in section 1.6. So very useful, so we don't have to prove both directions, so to speak. But what I want to close with then is this equivalent statements theorem. We have proved the first 4 statements are equivalent, but now we can add the next 2. And I'll just jump down to the end. AX equal B has exactly one solution for every n by 1 matrix B. Well, we just proved the theorem that if A is invertible, then AX equal B has exactly one solution. right? And if ax equal b has exactly one solution, we can prove that a is invertible. And so it's connected in. Well, what's the, if ax equal b has exactly one solution, then ax equal b is consistent. That's what it means to be consistent, that it has one or more solutions. And so, and in fact, it turns out we can prove that if ax equal b is consistent, right, where a, for every n by 1 matrix B, then ax equal b we can show has exactly one solution. I'm not going to prove that, but these are all now connected together. So this is our big theorem. Now we have 6 statements. And I would like you to be able to know all of these statements. In fact, usually what I'll say is, given that A is invertible, give me equivalent statements. And you can give me these 5. Also, these are important for true-false type questions as well. And one of the things about true-false, remember, these statements are equivalent, meaning they're all true or all false. So we know what they are if they're true, but what are the resulting statements if they're false? In other words, if A is singular, which means it's not invertible, then all these are false, right? So this statement, A is invertible, now is what? A is singular, right? Or A is non-invertible. What about this one? How do we make B false? B says AX equals 0 has only the trivial solution. Well, be careful. You can't say that AX equals 0 does not have the trivial solution is how we make that false, because AX equals 0 always has the trivial solution. The key word here is only. Okay, so to make this statement false, right, what would we say? We would say AX equals 0 has infinitely many solutions, including the trivial solution. Infinitely many, including the trivial solution. Okay. The reduced echelon form of A is the identity. What is this statement going to be if this statement is false? Well, it's a little bit more than the reduced echelon form of A is not the identity. Actually, we can say what? That the reduced echelon form of A has a row of zeros. Remember, for any square matrix, the reduced echelon form is either the identity or it has a row of zeros. And so if this statement is false, then we know that A, the reduced echelon form of A, has a row of zeros. A is expressible as a product of elementary matrices. Well, to make this false, we just say A is not expressible as a product of elementary matrices. That's the easy one. Now, AX equal B is consistent for every n by 1 matrix B, so be careful. To make it false, we would have to say AX equal B is what? If it's not consistent, we call it what? Inconsistent, right? Inconsistent system, meaning there's no solution to the system. So AX equal B is inconsistent, but it's not for every n by 1 B. You know, again, if I say a statement, I say everybody is a Tennessee Volunteer fan. Every person is a Tennessee Volunteer fan. Does that mean to disprove that I need to show that everybody is not a Tennessee Volunteer fan? No, I just need at least one person, right? At least one. If I find one person that's not a Volunteer fan, then I can't say everyone is a Volunteer fan. So same thing here. If AX equal B is consistent for every n by 1 matrix B, then to make it false, AX equal B is inconsistent for at least one n by 1 matrix B. And same thing here, AX equal B has exactly one solution. To make this false, we would say AX equal B has what? If it doesn't have one, it has what? Either none or infinitely many, right? So AX equal B has no solution or infinitely many solutions for at least one n by 1 matrix B. Okay, so those are the ways that we can restate those. So you'll get plenty of practice with that, thinking about the true-false statements in the homework. So memorize these, know these equivalent statements, and then use those in those true-false questions.